Hi, today we're going to be looking at the friction force, the force of friction between two solid surfaces. We of course have looked at this in class already several times, but we're going to learn a little something new about how we calculate the force of kinetic friction between two surfaces. So let's first of all remind ourselves that friction comes in two sorts: static friction, which we refer to as grip. And this occurs when you have two surfaces. So for instance, if you have an incline and a box is placed on an incline, and yet it doesn't slide down the hill, that's because there's a gripping effect between the surface of the box and the surface of the incline. And we actually have a static friction force upward, which is a static friction force, and that is preventing the box from slipping. So the box is gripping to the incline, if you will, and it doesn't slip. There are a lot of examples of static friction, but today we're actually going to focus mostly on kinetic friction, and that is what occurs when, obviously I can't write and talk at the same time. That's what occurs when you have one surface sliding or moving relative to the other one. We'll come back and look at static friction in a little bit more detail in another day or two. But kinetic friction occurs, as we say, when you have, and now I'm going to have a level incline, level surface. This is the floor or a tabletop, anything like that. And let's consider this box, for the sake of argument, let's say that it's sliding to the right. So I'm going to put a velocity arrow. And for the sake of argument, I'm going to say it's going at a constant velocity to the right, which means that someone has to be pushing it. So it could be a person back here who's pushing the box along. And because the box is moving to the right, the box has whoosh lines, which are very colorful blue. And it's experiencing friction between the box and the floor. And as I say, that's what we're going to study in a bit more detail today. So let's start by considering this box and labeling all the forces on it. And I would actually ask the video to pause for a moment and for you to just remind yourselves to draw a sketch in your notes of this box, draw a free body diagram, and draw all the forces acting on that box along with what is exerting them. And when you're done, we'll pick up the video again. Okay, I'm going to assume that you have done this now. And so let's do a quick review of what these forces are that the box experiences. So I'm going to do my free body diagram over here. And I have a force of gravity exerted by the whole friggin' Earth. I have a normal force upward exerted by the floor. I have a friction force to the left. This is the kinetic friction force, also exerted by the floor. And then there's the force to the right exerted by the person, which is keeping the box going here, exerted by the person. And so those are all the significant size forces acting on that box as it slides. Okay, what we're going to look at today, is, as I said earlier, is that we're going to learn a new way that we can calculate the force of friction. And we're going to make use of, and as we see now, this is a reproduction of a chart which is on the front page of your reference table. And this chart might not be very legible. This might help a little bit. But this is on the bottom right of the front page of your reference table, and it's a list of what we call approximate coefficients of friction. Okay, what are these numbers? First of all, I point out that this has two lists, a list of coefficients of kinetic friction and static friction. And again, for today, we're going to focus on the kinetic friction. We'll come back and look at static friction at a later time. So we're just going to, for right now, I'm going to cross these out. They're important, but we're not going to look at them today. What are these values? What are these coefficients of kinetic friction? What are these numbers? Well, the first thing I notice is that these are quantities. This is a quantity. These are values on a physics reference table, and they have no units. Well, we're going to see why that's the case in a second, but it's worth noting that coefficient of friction has no units. So there will be one time you can leave a number naked. The second is that these values on here, they happen to all be decimals. It is possible to have a coefficient of friction greater than 1. These all happen to be between 0 and 1, so they're all point something. And so let's look at the numbers that we have here and see if we can figure out what the heck they mean. I've got some numbers that are as high as 0.68 and 0.67. Those seem to be about the highest. And the numbers go as low as 0.05 is a pretty low one. 0.04 is a little bit lower. So I've got numbers that vary from 0.0 something up to 0.67, 0.68, almost 0.7. I also notice, of course, that there's a list of, materials here on the left that correspond to each of these numbers. And if I look at these materials, let's see, I've got rubber on dry concrete. Right below that, the one that also has a high coefficient of kinetic friction is rubber on dry asphalt. Those are not just random materials. These are the materials you find on the tires of cars and on pavement. Okay, when you're driving a car, you're driving a car with rubber tires, and those tires are in contact with dry concrete or dry asphalt, dry pavement. And these values have fairly high coefficients of kinetic friction. The lower values, I've got one here for waxed ski-on snow and another one for Teflon on Teflon. Teflon, if you're not familiar, is the material that is used for non-stick coatings on cookware. So if you have a Teflon fry pan, it's very, very slippery. Well, yeah, these two surfaces, wax ski-on snow and Teflon on Teflon, are things that we would call very slippery. Places where you have very little friction. Whereas the two that have the highest coefficients, rubber on concrete and rubber on asphalt, are, I guess I'll call these grippy, even though we are talking about kinetic friction. I'll put quotes around that. I just don't really have a good word for not slippery. And so, okay, what do we know so far? We know that these coefficients of friction have no units. We also know that they are paired with not even just one material. Every one of these has material number 1 and material number 2. Rubber on ice, material number 1, material number 2. These coefficients of friction all go along with a pair of materials. And these pairs of materials would be the pairs of materials that are in contact with each other when you have a kinetic friction force. So for instance, if in this diagram up here, if this box is made of wood, and if the table is, or the floor is made of wood, then if I were going to be considering the kinetic friction force between these two surfaces, I would use the wood on wood coefficient of kinetic friction. I haven't said yet what we're going to do with it, but if I see a wood box on a wood table, then I know that I'm going to be dealing with a coefficient of kinetic friction that corresponds to wood on wood. So all these different values correspond to pairs of materials that are in contact with each other, and since we're talking kinetic friction, these kinetic friction value coefficients correspond to pairs of materials that are sliding relative to each other. And so we're seeing that these kinetic friction coefficients of kinetic friction, are dimensionless values. They have no units, and they correspond to pairs of materials. And the numbers seem to be low for slippery materials, and they seem to be high for not slippery or grippy materials. That's a good conceptual understanding of what these numbers are. They're numerical descriptions, if you will, of how slippery two surfaces are. So let's just say a couple facts about these coefficients of friction. I'm just going to write a couple of facts. These are sort of conceptual facts or bookkeeping facts. The first fact is that a low value means that these two materials are slippery when in contact. So that would be a low coefficient of kinetic friction. Two, I remind you that they have no units. It's a dimensionless quantity. The third is we are going to be putting these values into formulas, and so I will tell you that the abbreviation for this quantity is a Greek letter, actually, and it's the Greek letter mu. It's a small case mu. It looks kind of like a U with a tail on the front. When I say mu, spell the name of a letter, which may or may not be ironic. This is a Greek letter spelled mu, mu. Okie doke. So what do we do with this? Well, you can simply recognize that a low coefficient of friction means the two surfaces are slippery, and a large one means that they're not. But we, of course, will be using this in a formula and doing calculations with it. If you want to look on the back page of your reference table right now, you can find that formula. And it's about halfway down the list of formulas on mechanics. And it looks a little something like this. Friction force equals mu, coefficient of friction, times the normal force. And I do want to point out something very, very important about this formula. First of all, as many of the formulas have been that we've been doing with forces, we're only going to be putting magnitudes of values, which means no clouded code when we use this formula. So that's one thing. You're only going to be putting numbers and units in there. Of course, no units for mu. And the other thing that is very, very important to understand is that when you apply this formula and you use this to calculate a force of friction, and if I go back to this situation that we were looking at before, pushing a wooden box across a wooden table, if I look at the free body diagram for this situation that we're looking at here, I actually see that there are two normal forces exerted on this box because the box is in contact with two surfaces. It's in contact with the wooden floor, and it's also in contact with the person's hands who are pushing it. If you're putting numbers into this formula for friction force equals mu times Fn, which normal force do you put in to calculate a friction force? And here's the key thing. To use this formula correctly, these two forces must be exerted by the same surface as each other. So in other words, these two forces have to come from the same two surfaces in contact. What that means up here is that I would not put the friction force exerted by the floor into a formula with this normal force exerted by a person. I would not put those in the same formula. I have to put the friction force exerted by the floor along with the normal force exerted by the floor. These two forces both come from this surface of contact between the wooden floor and the wooden box. Those are the two forces that go together into that friction formula. Okay, how do we actually use it now? Let's take a look at an example problem. This will be example number 1. And a very simple problem using this formula would go something like this. A normal force of 12 newtons exists between two steel surfaces sliding across each other. This is a poorly worded question, but that's what you get. And then they say calculate the force of kinetic friction. Okay, so you look at the problem and you say, okay, they gave me a normal force right here of 12 newtons. And then they didn't give me a coefficient. What they did is they gave me two steel surfaces. So you've got, this would be like a steel table, which we all have in our houses, and a steel box sliding on that steel table. It's got whoosh lines. This is steel, and this is steel. And we need to find the force of friction between them when the normal force exerted between them, so this normal force exerted by the table, is equal to 12 newtons. Okay, how do we do that? Well, I write the formula. Friction force is mu times normal force. And I don't know what mu is, and that's what the chart is for on the front page of your reference table. You will notice that we have on the reference table one listing for steel on steel, and it has a coefficient of kinetic friction of 0.57. So that would go into our up chart. We have a normal force with a magnitude of 12 newtons. We have a coefficient of kinetic friction of 0.57, and we can calculate the friction force by plugging those into this new formula. Friction forces are unknown, and that's going to be 0.57 times 12 newtons, and we get a friction force of 0.57 times 12, which is going to give me an answer of, pressing buttons, 0.57 times 12 is equal to 6.8. I'm going to round it to 6.8 newtons. You can see here possibly why it is that the coefficient of friction doesn't have units, because it's just a multiplier, if you will. It's basically telling you what you got to multiply one force by to get another force. So it doesn't have units. It's just basically a multiplier, a percentage, if you will, that tells me that if you have steel box on a steel plate, the friction force is 0.57, or about 57% as big as the normal force between them. All right, I'm going to do one more example problem, because of course these can get a little bit tougher, and here's how they could do that. Okay, if you have, here's example 2. And here we have a wooden box sliding whoosh lines on a wooden table. And if I tell you that the mass of the box is 6 kilograms, and if I ask you what is the force of friction, calculate the force of friction between the box and the table, how would you do that? Okay, I'm going to ask that you pause the video now and see if you can figure that out. What is the force of friction between the box and the table? So take a few minutes, pause the video, and when you guys think you have it, fire it back up and we'll work it through. Okay. Okay, so how do we do this problem? Well, I'm going to work backwards. This is a multi-step problem, and I'm going to work backwards from what I want to get to what they give me. I want the force of friction, FF, equals question mark. Okay? And there are two ways actually I could get this. One would be if I happen to know something about the other force possibly pushing this thing forward and whether or not the box is accelerating. So in other words, one thing I could do is if I have a free body diagram of this box, I've got a force of gravity down, exerted by Woofy. I've got a normal force up, exerted by the table or floor or whatever that is, the wooden surface. I definitely have a friction force to the left, exerted by the table, wooden table. And you know, I don't know if there's a force to the right or not. They never told me if this box is someone's pushing and it's going at a constant velocity, or if someone pushed it earlier and now it's just sliding to a stop. I guess I have to assume there's no force at all, but in this case I can't actually learn anything about what the size of the friction force is based on any force in the other direction, because I don't know if there is one, or I have to assume that there isn't. So what I have to do instead is use the new formula that we have. Friction force is mu times the normal force. And can I get that? Well, let's see. It's sliding, so I know I'm using kinetic friction. I need mu, and I do know that because if I go back up to the chart, which is on your reference table, wood on wood has a coefficient of kinetic friction. Make sure I'm using kinetic because it's sliding, of 0.30. So I'm going to plug in 0.30 as a coefficient of kinetic friction. And let's see, do I know the normal force? I don't. Now the normal force I'm looking for is the one which is exerted, the force between the table and the box. I don't know how big that force is, What else did they give me? They gave me the mass of the box is 6 kilograms. Let's make sure I don't put that in as a force. That's not a force. That's the mass of the box. Is there any way I can use that to calculate the normal force? And in fact, there is. Because here's the thing. I know, I'm going to use my knowledge of dynamics and Newton's laws. I know that there is no acceleration of the box up or down. Okay, it's not accelerating vertically. That tells me that these two forces, the normal force and the gravitational force, are balanced with each other. They have the same magnitude in opposite direction. So if I can calculate the gravitational force, then I know that that has the same magnitude as the normal force. And that, once I know that, I can put it into this formula and calculate the friction force. So can I calculate the gravitational force? Well, yes, I can. The gravitational force is mass times acceleration due to gravity. And the mass is 6 kilograms. The acceleration due to gravity on Earth is 9.8 meters per second squared. And that gives me a 58.8 Newton force of gravity. That's how much the box weighs. All right, the box isn't accelerating up or down, so that's in balance with the normal force. I now know that the normal force is 58.8 newtons between those two surfaces. So now I can finish this calculation of the friction force by multiplying the coefficient of kinetic friction, 0.30, times the normal force, 58.8 newtons. And the force of friction, then, is 0.3 times 58.8, which my calculator tells me is 17.6 newtons. Okay, that's the force of friction. That makes me happy. And that's it for this video. Thank you very much.